In this video, we will take a known molecular formula, a known molecular weight, and construct an adequate molecular structure based on MS, IR, proton NMR, and carbon-13 NMR spectra. The first thing you want to look at when you're given a molecular formula is degrees of unsaturation. And given the formula C6H6O2, we find 4 degrees of unsaturation. When we see 6 carbons and 4 degrees of unsaturation in a molecular formula, we immediately want to think of a benzene ring because they're so commonly found in nature. When we look at mass spectra, the most important piece of information we'll get about our molecule is the molecular weight. The signal furthest to the right on the spectra is going to be our M+ signal, or the molecular ion signal. This corresponds to the molecular weight of the molecule, and since we were given that ahead of time, we can see that that corresponds perfectly. The next thing we can look at is our base signal, or we can look for the most intense signal, or the highest signal on the spectra. The base spectra tells us the most common fragment that is made as the molecule is broken apart in the mass spectrometer. When we see that the M+ signal and the base signal are the same, that tells us that our molecule is very stable, it's not readily broken apart, and we can first think of an alcohol. So if we hypothesize a molecular structure given our formula and our molecular weight, we can start with the benzene ring with 4 degrees of unsaturation, and we can turn that into an alcohol. We know we have 2 oxygens to account for, 6 hydrogens, and 6 carbons. So we can come up with a hypothesized structure that looks like this. Moving on to IR spectroscopy, we can get clues as to functional groups of our molecule. And the first thing I like to do when I look at an IR spectra is draw a line right around 1500. I know that I'm going to concentrate to the left of this because that's the diagnostic region of the spectra. The easiest functional group to identify in IR spectra is an alcohol, and it's a broad and strong signal above 3300, and we see that here. So we know that we're going to expect to see an alcohol in our structure. The second signal I want to focus on is right down here at about 1520, and we know that that is in the CC double bond region. The third area I want to look at is right above 1600, and it's an area of small peaks. This is usually indicative of an aromatic structure, so I just wanted to point that out. When we look at our hypothesized structure towards the bottom of the screen, we can see that we do have alcohol in our structure. We can also see CC double bonds. And we also have an aromatic. So we can compare our hypothesized structure to the signals we're seeing in IR, and all of this makes sense. Next, we'll move on to proton NMR. Proton NMR gives us a lot of information about hydrogen groups on our molecule. First, we want to note on our spectra that to the right is the lowest number, and that is going to be upfield. All the way to the left, that is known as downfield. Each signal corresponds to a different type of hydrogen group. So on this spectra, we see 3 signals indicating 3 different hydrogen groups that are experiencing different environments. Each signal also tells us how many hydrogens are in each group. So we see that each peak shows 2 hydrogens. So when we add those up, we get a total of 6 hydrogens, and that corresponds to our molecular formula. Next, we can look at how many peaks are in each signal. And we follow the formula N+1 to calculate the number of peaks found in each signal. N is the number of neighbors that each hydrogen group sees in the structure. So if you have 2 neighbors, plus 1 would be 3 peaks. When we look at the peak furthest downfield, we see that we have 1 peak. This means these hydrogens will see 0 neighbors. We also see that this hydrogen group is the furthest downfield. So these are the hydrogens that are going to have the most de-shielding. We're going to zoom in on the two hydrogen groups found more upfield so we can look at their peaks in further detail. We see that the signal on the left has 4 peaks, which means that group is going to see 3 neighbors. And then moving to the right, we see that that group also has 4 peaks and is going to see 3 neighbors. It's also important to note that these 2 peaks are found in the 6 to 7 range, and that's going to tell us that they are going to be attached to an aromatic. These 2 hydrogen groups are going to be found close together on the structure, and this group to the left is going to experience a little bit more de-shielding than the group on the right. So let's compare our structure to the signals that we see on the NMR spectra. We see that we do have 3 different types of hydrogens in 3 different environments. So starting with the hydrogens circled in pink, we see that they do not see any neighbors. And they are going to experience a significant amount of de-shielding because they are attached to electronegative oxygens. So the hydrogens circled in pink are going to correspond to the signal most downfield. Next, let's look at the hydrogens circled in blue. They're going to experience the least de-shielding because they're furthest away from the oxygens. So they are going to correspond to the signal most upfield. And lastly, the hydrogens circled in green are going to feel de-shielding somewhere in the middle. So they are going to correspond to the signal in the middle. Finally, let's take a look at carbon-13 NMR. Carbon-13 NMR is analyzed much the same way that proton NMR is, but you're not going to see any peaks on your signals. Each peak is going to correspond to a type of carbon found in your molecule, and the chemical shift will tell us how these carbons correspond to each other or where they're located in the structure. So the carbon-13 NMR spectra shown here is going to tell us that we're going to have 3 different carbon groups. Much like proton NMR, the carbon group found furthest downfield is going to experience the most de-shielding, and the carbon group found furthest upfield is going to experience the least de-shielding. When we look at the chemical shift of each carbon group and compare it to the corresponding table, we see that we're going to have CC double bonds, and we're also going to have an aromatic molecule. When we look at our hypothesized structure, we find that we in fact have CC double bonding in the aromatic benzene ring. When we compare our structure to the spectra, we also see that we do in fact have 3 different types of carbon in our molecule, each experiencing a different chemical shift. The carbons closest to the hydroxide groups are experiencing the most de-shielding due to the more electronegative oxygen atom. So those carbons are going to correspond to this signal. The carbons circled in green are going to experience the least de-shielding because they are located the furthest away from the oxygens. So they are going to correspond to this signal. And lastly, the carbons circled in pink are going to feel de-shielding somewhere in between the blue carbons and the green carbon. So they are going to correspond to the middle signal. In review, we can be given a molecular formula and a molecular weight. Then, with information based on MS, IR, HNMR, and carbon-13 NMR spectra, we can construct an adequate molecular structure. In this example, our hypothesized structure proves true and is an alcohol known as catechol. Catechol occurs naturally in fruits and vegetables and is part of the reason why apples and potatoes kind of turn brown when they're left open to air once they're cut open. Artificially, catechol is used in flavorings, fragrances, and pesticides.